In this video, we're going to derive the formula for torsion as it relates to calculus 3. Now, by definition, torsion is equal to this, right? It's basically this dot product, the dot product of the negative derivative of the unit binormal vector with respect to arc length and the unit normal vector. And the whole idea of this video is to go from the definition of torsion to proving torsion is equal to this. And as you can see, this formula is completely in terms of the position vector. So our goal is to re-express this completely in terms of the position vector. And remember, all these primes really mean are basically the first, second, and third derivatives of the position vector with respect to t. So that's our goal in this video, is to prove this formula. So to start, we should probably bring t into the picture. And we can do that by doing this. So this is basically what we've done. And going from here to here is the same thing as saying this. It's basically one of the major ideas from taking the derivative of a parametric equation. And so that's really the concept that we're applying right here. And so that's the idea. Now we can rewrite the numerator as negative b prime. But what do we do about the denominator? Well, from the definition of arc length, this is basically what it is. But if we take the derivative of arc length with respect to t, then really we're just using the fundamental theorem of calculus. And so we see that all we're going to be doing is we're going to have exactly what we have here, but we're substituting the u with t. And so this is all ds over dt would be. And we don't really need the t right there because when we see a prime, we can assume it's taking the derivative with respect to t. So we're just going to write this right here. So this is what we have now. But really, this is a dot product, so we can pull out the scalar to the front. And this is where we're at. So now what we need to do is express b prime and n in terms of the position vector. And then simplifying whatever that is, we will get to the formula for torsion that we're looking for. Now, we're going to start by first figuring out what b prime is in terms of the position vector. And so to find b prime in terms of the position vector, we're first going to start out with b in terms of the position vector. So if you recall, this is the way that we can express the unit binormal vector completely in terms of the position vector. So all we got to do to find b prime is take the derivative with respect to t of both sides. And so really, this is just b prime, but all we got to do is differentiate this. Now, I'm going to rewrite this slightly differently so you can really see what we're about to do. And the reason why I've expressed it this way is because you can now see that we're really just going to be using the product rule. If you recall from the product rule, it goes derivative, no derivative, plus no derivative, derivative. So using the product rule, here's what we're going to get. So this is what we would get when we use the product rule. Now, to evaluate what this is, we're first just going to start by finding this derivative, because this one looks a little bit more complicated. Let's just figure out the derivative of this cross product. If you recall, from the derivative of a cross product, all this is going to be is if we were to use the product rule. And that's the idea. We're basically going to apply that same idea to what we're doing right here. And so evaluating that, really we're going to take this and apply it to what we're doing right here. So what we're going to get is this. So this is what we get. And really, the cross product of a vector with itself is just 0. And so really, we're just going to replace this with what we have right here. So the next thing we would have to do is take the derivative of this. But here's the thing, we actually don't even have to do that. And the reason why is because if we decide to get the unit normal vector involved, in other words, we're going to take the dot product of n on both sides of the equation, right? So this is basically what we're doing. But here's the thing, this is a dot product now. It's a dot product between n and two vectors that are added together. And remember, the dot product is distributive, so we can distribute the n to both of these terms. Now, here's the thing I want you to really see. When we take the dot product of this first term with the unit normal vector, it's going to result in 0, right? Because this right here is really our vector quantity. This derivative is a scalar quantity because when we're taking the derivative of a scalar, that will result in a scalar. So really, our only vector quantity in this first term is r prime cross r prime prime. Right? And r prime cross r prime prime is parallel to the unit's binomial vector. If you recall, the unit binomial vector and r prime cross r prime prime point in the same direction. And when we take the dot product of the unit binomial vector and the normal vector, this is going to result in 0 because these two vectors are perpendicular to each other. And since this vector points in the same direction as the unit binomial vector, that means when we take the dot product of this vector and the unit binomial vector, that will also result in 0. And that's why when we take the dot product of this term and the unit normal vector, it results in 0. So this term doesn't even matter, right? So taking the derivative of this, we don't even have to do that. So this, the dot product of this and n becomes 0. So we can disregard that term completely. So really all we have now is the dot product of the second term and n. And by the way, this is a b prime. So this is what we have now. But we're actually going to convert this back into torsion. All we got to do is multiply this by -1 over magnitude of r prime. So this is what we have. But remember, in the beginning of what we were doing right here, our whole goal was to find b prime in terms of the position vector. Now we have to express what n is in terms of the position vector. And if we recall, n is equal to this. Right? This is basically what the unit normal vector would be in terms of the position vector. Now, if you don't know where this comes from, I actually did make a video on showing why this is true, but really all this is doing is taking the unit binomial vector and crossing it with the unit tangent vector, as you can see. That's really all this is saying, because the unit normal vector is the cross product of the unit binomial vector and the unit tangent vector, which is really where this comes from. But really, we're going to substitute the unit normal vector for what we have here. But we're gonna write it slightly differently, right? We're just gonna put a 1 right here and move our vector out to the front right here. And this is what we're gonna substitute n for. And this is really what the unit normal vector would be. So this is torsion completely in terms of the position vector. So now we basically need to condense this as much as we can. So the first thing we should do is, well, first, notice how this really is a dot product, right? And for each of these two vectors that we have right here, there's a scalar in front of them. So we can pull those scalars out of the dot product. So this is our scalar. And for the vectors, right? So this is what we get when we pull out our scalars. Now I'm actually going to move back up to the top. So this is what we have now. Now there's a lot going on here, especially with this dot product. It's like, how can we even condense this? Now, really, it turns out that in this dot product, we can actually pull out a magnitude of r prime squared. And that magnitude of r prime squared will cancel out with the one we have in the denominator right here. So really what we're gonna do is we're gonna focus on this dot product. That's really what we should be focusing on right now. So, focusing on this dot product, we're going to try to pull out a magnitude of r prime squared. What I want you to notice here is that this is in the same form of a scalar triple product. What I mean is, if we call this vector vector u, this vector vector v, and we'll just say this is vector w, really, this is in the same form as this, right? And this is the form of a scalar triple product. So if you recall, if we basically interchange the positions of any two vectors, this value just becomes negated. Now we want to pull the r primes out of the dot product so we can really pull out a magnitude of r prime squared. So we're going to interchange the positions of u and w. And so again, from the scalar triple product, this statement would be true. And so we're going to apply this idea to what we're doing right here. So this is what we have now. So now we're going to want to focus on this cross product right here. And really what I want you to notice is that this entire thing can be represented as a vector triple product. In other words, it's in the same form as something like this. And if we recall, from the vector triple product, this would be equal to this. And so now we're going to apply this idea to what we have. And so this is what we get from the vector triple product formula. Now, notice how for our second term right here, this just becomes 0 because r prime is perpendicular to r prime cross r prime prime. So what we're left with is everything we have right here. And notice how all this is a dot product between two identical vectors. This can be expressed in the same form as this. That's basically all it is. And again, we could just pull our constants out. And really, v dot v is the magnitude of v squared. And we're really just going to be applying this idea to what we have here. And this is where our magnitude of r prime squared comes from. And so now all we're going to do is substitute this for what we have right here. And so this is really what we get. Notice how in these brackets, really all this is a scalar times a scalar. That's all it is. And so really what we have is the magnitude of r prime squared and the magnitude of r prime squared cancel out. The two negatives multiply together to become positive. So now you can really see what we have left in the numerator. In the numerator, all we have is this. And in the denominator, it's the magnitude of our cross product squared. And this is the formula for torsion. And we've basically proven it. We've gone through basically here, re-expressing b prime and n, and then focusing on this, using the scalar triple product, the vector triple product, and now we've made it to the formula for torsion. And as you can see, it did take quite a bit of work to do so. But really, we took a shortcut when we took the dot product event, because really, we saw that we didn't need to take the derivative of that one thing. And so this allowed us, even though we still had a lot of work to do, we still ended up figuring out the formula for torsion. And that's the whole idea of how we could derive the formula for it. And that's pretty much it.